So we had started looking at the levels of organization, or basically how we build our protein. And remember that the key here is structure equals function. Okay? And this is how, when we think about proteins having that really wide variety of functions that they can do, if we're going to get that wide variety of function, we have to have a wide variety of structures. Okay? So really that's the key here when we're looking at these things, is how exactly can we construct so many different shapes of proteins. Okay? That's why we have seemingly so many more stages for protein than we did for making a carbohydrate, or making, making a lipid, which were simply just throw a bunch of dehydration syntheses together and you get a big lipid, right? All right, so let's focus again here. We're going to look at the primary structure. So again, the primary structure is this. Let's use a bunch of dehydration synthesis and throw these bad boys together. Okay, so as we're linking together our amino acid sequence, right, this is using that dehydration synthesis. So this is, all this is creating those peptide bonds that we did creating a couple slides ago, right? Jane plus Carl. Oops, poor Jane, almost lost a letter. Losing arms, losing letters, okay? Okay, what are the two elements that a peptide bond are between? Carbon and nitrogen, good. Right, remember, that's what makes a peptide bond unusual. So instead of being a carbon to oxygen, right, that normal hand-holdy bond that we have, okay, we had a carboxyl group and the amino group that we were doing the dehydration synthesis between. Right? That amino group is weird, okay, but it still works because the amino group can give us a hydrogen. That's all we need, making water. But it does leave the carbon holding hands on a nitrogen, the nitrogen being from that amino group. Okay. So we said this looks a bit more like we're sort of intertwining on that elbow. It's that weird elbow grip. Okay. New shape, new name. All right. So just like when we did lipids, we did dehydration synthesis, we had the hat. Right, the double bonded oxygen sitting on our carbon, so it was called an ester bond. Okay. This has that nitrogen there. Okay. Slightly different look, same process, but it's a different look, so it gets a different name, the peptide bond. Okay, so this is exactly what we normally think of when we're building our structures. What we do with carbohydrates, this is what we do with lipids. Okay, so all we're doing is taking, pardon the swiping, all of these different amino acids, get that out of there for a second, okay, any different one, right, the more variety the better, okay, and linking them up in that chain, okay, using dehydration synthesis. Okay. Remember, the other key here is that we are two-dimensional. Okay, so that's what we mean by, pop this back open, being linear or flat. Okay, and this two-dimensional versus three-dimensional thing will be very important. Okay, so we're two-dimensional. We're just constructing my string of pearls. Right, so we're very flat. Okay, that feel okay? Okay, so this is usually all we think about. We stuck a bunch of carbohydrates together, we made a longer carbohydrate. Okay? We stuck a lot of lipids together, we made a longer chain of lipids. Okay, so we've stuck a lot of amino acids together, made a longer chain of amino acids, or a polypeptide, right? So that's our primary structure of organization. Any questions about that before I move on? Does this feel okay? This is our more or less our solid footing. We're familiar with this process. Bye-bye. Okay, so where we left off on Wednesday was the secondary level. Okay, so we're taking that chain of amino acids, right, those linked beads, and all we're going to do, right, is either twist or kink them. Okay, remember, we're still flat. Okay, so we're just kinking them in our 2D plane, or we're rolling them in our 2D plane. Okay, but we're still not coming up in a three-dimensional way. Okay, and so we have this helix or pleat name that goes with it, right? The twists is the helix, the pleats are the kinks. Okay, so remember we talked about for our strands, you will have both of these. Right, because remember, when we think about linking these polypeptides together, we're not just going to link 10 amino acids in a row. Okay, you'll have hundreds or thousands of them in a row. We're going to make quite long chains. Just same when we talked about carbohydrates. We can say one too many, and that many doesn't usually mean 3 or 4. It usually means hundreds or thousands. That's why we're lazy counters, right? That's the same thing here. So if I have a polypeptide that is 1,000 amino acids long, okay? The first 100 might be an alpha helix, so I might have nice little twirls, okay? Then the next 100 may be kinks, and then the next 100 we may go back to twirls again, okay? So we'll have discrete sections where I would go back and forth between. Remember, these are held by hydrogen bonds. Okay, so we call these the leftovers. So remember, if we think about our carboxyl group, okay, so that normally looks like this, right? Ooh, I should come back on screen. No, I'm sorry. It's fine. The way you're sitting is fine. When our carboxyl group was used for dehydration synthesis, right, to link all of ours together, we lost this, right? That went to water. That was our first H and O, right? And when we think about our amine group, which I've drawn very poorly, that's how it looks, right? Okay, we also lost an H to the water during dehydration synthesis, right? Okay, that's how Jane and Carl held hands. Okay, and these C's and O's, blah, 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 are hooked up and all of that business. Okay, so these hydrogen bonds are held on by the leftovers here. And by leftovers, and this is where we left off on Wednesday and why I wanted to back up a little, I'm talking about these oxygens and these hydrogens. Okay? They're not being used for anything right now. Okay, the carbons and nitrogens, okay, are connected, they're bonded. Okay, our hydroxyl and hydrogens at the bottom are gone, but our double bonded oxygen and that leftover hydrogen are just hanging out. Okay, riding the waves. Everybody has ignored them up till now. And they don't want to be ignored anymore. Okay, so our oxygens and hydrogens, well, no, we already used blue. It's green. Let's use green. Are attracted to each other. Okay, and we've seen this before, right? This is why polarity works. Right, the oxygens from there are attracted. So the oxygens from the double bond are attracted to the rogue hydrogens. And this is a decently strong bond. Okay, so these connections are what pulls and folds our secondary organization into these twists and kinks. Okay. It's like the Lonely Hearts Club. Okay, they've been left out till now. They need someone to hang out with. Okay. So all along our structures, if we focus over here, green works. Okay, we can see, okay, there's one of our rogue double bonded oxygens, okay, being attracted to, okay, that leftover lonely heart of a hydrogen. Okay. And that's going to happen all over our structures, same thing here. Anytime those oxygens and hydrogens are close enough together, they're going to end up pulling in and hydrogen bonding. Okay, it's called a hydrogen bonding because we're attracted to that hydrogen. Does everybody see that?
Do the oxygen and hydrogen end up bonding, or do they just attract? Or they just want to bond?
It is a type of bond. Good question. Okay, any questions about hydrogen bonding? Okay, this connection between our rogue oxygens and hydrogens that's making our alpha helices, or our twirls, and our beta pleated sheets, or our kinks. And I know the alpha and the beta feels kind of counterintuitive. It's just kind of like counting in chemistry. We discovered the helix first, so that's alpha. Just literally the first letter in the alphabet for Greeks, and the beta. It's not something I'm ever going to ask you. I'm not going to make you draw, in case you're wondering where that came from. That's all that is.
So there's a question in the chat that says, so the oxygen is always attracted to the hydrogen.
This is correct. So the question in the chat was, and I'm going to put it by the mic here, the oxygens are always going to be attracted to the hydrogen. So for this level, right, the oxygens are slightly negative, right? These are the selfish roommates. They're kind of hoarding the electrons. And the hydrogens are slightly positive, okay? And so because of that, these guys are always attracted exclusively to each other on this level. It's a good question. Okay, they're very faithful pairs. So no. We'll get there. Her question is, are they only going to be attracted to each other at the secondary level? We're actually going to see them rise their little fingers up in later levels as well. This is the first time that we're going to see them pop up, so they're not important at the primary level. And they're the only thing that's happening at the secondary level. But they will show up again at the third and fourth. Right? Because this is a really strong bond, and they are highly attracted to each other. So pretty much any time you have loose hydrogens and oxygens, this is going to happen. Great questions. And right now, that's the main thing that's going on. So this is the strongest interaction we have. Okay, any other questions? I don't know what to do with this thing. Anybody sneezed in their mask yet? That's a fun one. You still put your arm up and it doesn't matter and it just like splatters all over your face. Great. Okay, any questions about primary and secondary levels of organization? Okay, so what we have now is a very long chain of connected amino acids, okay, that is flat but sort of rolled or kinked in on itself, right? Sort of like when you're a kid and you made this sort of like accordion folded paper things, right? Laid flat on the table but it kind of kinked up. Like the legs for those like people things you made in elementary school. Okay. Yes, thank you. I like the drawing thing now. All right, so let's look at tertiary structure of organization. Okay. So the big thing to remember at tertiary, okay, so this is our third level of organization. And now we're 3D. Okay, so what we've done now is we're going to make a three-dimensional shape. And once we created a three-dimensional shape, we are a functional protein. Okay, which means this protein, whatever it is that is done once we've folded and twisted this thing up, can go out and do its thing. Whatever that is. Okay, so if we've created a protein channel, okay, this can go be embedded in our plasma membrane and move things around in the cell. Okay, if we've created an enzyme, this can go out and break down milk sugars.
So there was a really good question in the chat. Somebody said that I thought that secondary was 3D since it was folded and twisted.
So we're kinked, but we're kinked flat, right? So we want to imagine that piece of paper on the table, right? And all you've done is sort of pleated it up. So imagine pull my sticky out here. I'm going to go ahead and put some pleats in my piece of paper here. It's a great question. Really poor, very fast pleats. Which are obviously not of equal size. Make sure this is big. All right, great question. Give me a hot second. Okay. So if this piece of paper is originally, right, my polypeptide chain, so it's flat. We'll pretend it's very, very long. That's what I got on me. I'm doing this on the fly, right? So if it was very, very long, right, the longer it is, the longer my primary sequence is, right? Because I can just keep adding and adding and adding those amino acids. Okay. When I get to my secondary sequence, where I'm putting my kinks and my twirls in it, so I'm going to put my kinks or my pleats. Okay. Now I've put a bunch of folds in it. Okay. So you can see that I complete this. Okay, so I have kinks, but it's still flat. Right, so I've kinked it up. Okay. So I've kinked it up, I've made a bunch of pleats, but I haven't created any significant three-dimensional structure. Okay. So this is really what we're talking about when we're talking about these alpha helices and beta-pleated sheets, right? We're still creating these hydrogen bonds, right? We've altered the shape and the connections of our primary structure. It's differently shaped now, okay? But we don't have, right, we haven't created any origami here. Whereas when we get to the third level, I can only do so much with paper, but humor me. Okay, this thing is going to twist and open, okay, as other additional, I know it's very beautiful, right? But as additional, and I'll show you the drawing again here in a minute, bonds and interactions are going to pull and twist it in other ways, okay, creating that three-dimension accordion shape. Okay, so we still have the pleats in there, right? We can still see them, but now we've also pulled it a third direction. Does that help clarify? Origami post-it. Yes. And the way we get that 3D structure, okay, wait, did I actually, there we go. Okay, or our origami is with those side chain interactions, which we have not used before now. Okay, so those R groups that we have all that diversity in, okay, those start to play a role. And they haven't played a role up till now because their bonds, for the most part, are a lot weaker than the hydrogen bonds we were just looking at. Okay. Now, what these actually are, remember, we have a lot of variety of choices. Okay. So we can just generally, it's going to look like a hot mess. Oh, no, we're good. Call them side chain interactions, right? Because this can mean any number of things. Okay. Some of which are going to be really familiar. So we already know that we have those hydrophobic interactions, right? What we saw with when we have those hydrophobic tails, right? They tuck themselves in the closet and hide, okay, like we saw with the phospholipid. Okay. We also talked about things like the ionic bonds, okay? Positive and a negative come together. We know those kinds of things happen. Okay. Somebody asked a great question about whether or not you'd see hydrogen bonds again. Positively. Okay. So there's any number of choices here, a list of which I will absolutely never ask you. Okay. What's key here is because of the diversity that we have, those things will all start to interact with each other. And that's what's going to pull and twist and kink this into that three-dimensional shape. Okay? And it ultimately ends up looking, origami is not bad. This is the first year I've ever thought of origami while doing it on the fly. I often think of it a bit more like taking your headphones, the ones that still have cords, and when you put them in your pocket, no matter what you do, how nice you do, and they come back out there with that kind of knotted ball. Right, so they were two-dimensional when you put them in, right, nice and rolled and twisted. But when they come out, they're a three-dimensional knot, right? And no matter how hard you try, it seems like it's almost worth throwing them away as opposed to unknotting them some days, right? Okay, so that three-dimensional knot, okay, of your headphones, and before the advent of iPods, I'm actually going to eventually have to come up with a new analogy here, is a lot like this ends up looking like. So it's holding all of those knots together, okay, and that massive ball is our side chain interactions, okay, the connections of all these different R groups. Okay, our non-polar or hydrophobic interactions, okay, a positive, a negative, And that makes it want to knot or ball up, right? Because positives are attracted to negatives, to non-polar deserts are attracted to each other because they need to hide. Okay, so it's been a long haul, but we have to have all three of these things in order to get a real large functional protein. Okay, our origami swan.
So do these exist like independently, or is this like a process that it starts as like the first level, then it goes to the second level, and it goes to the third? Or is it like you have first, second, and third?
I'm not 100% sure I understand your question.
Okay. So like, is a first, like, is a primary amino acid, is it going to transform into a secondary and then a tertiary?
Correct, yes. So it's a transformative process, right? So you will have these built from the ground up, like making a Lego tower. Okay, you have your individual pieces, then you make the base, and then you can make like this whole 3D structure out of it, and you would go start to finish with it. Okay, and conversely, right, when you're done using the protein, as we'll find, cells are not wasteful. Okay, so when you're done with it, you can break it down all the way back down to the primary structure and get rid of all the pieces. Cells are very good at recycling. Yeah, so you really want to think about this as a process, right? We started at the primary level, we linked all our Lego pieces together, right? Then we created our base, right? Then we were able to make a three-dimensional structure on that base. And then when you're bored with your Lego structure, okay, we can tear that down back to the main pieces and start over and make something else, right? And just like proteins, your Lego towers are made up of differently shaped pieces. And so how you construct those pieces together is going to give you different things. Like I made a plane, I made a tower, right? And it's all in what order you put the pieces together that's going to alter what that shape is. Okay, really good questions. Okay, any other questions? Okay, so that leads us to the coordinary, okay, our fourth level of organization. Okay. Now this seems a little strange because we just got done saying that at the third level we have a functional protein. So what do we have to do from there, right? We already made a working protein. It's going out, it's got a job, it's an adult, okay, working for the man. Okay. So coordinary proteins are very complex proteins. Okay. They do group work, which is everybody's favorite. Okay. So the coordinary of course, it just means fourth, like quarter. Okay. Means that we're taking completed third level. I just want to think about this as an additive or a growing process. We're going to take those completed or third level proteins and we're going to combine them together. Okay. So if I look at the example I have on here, this is a tertiary protein. This is a tertiary protein. This is a tertiary protein. And this is a tertiary protein. So the example I have is actually made up of 4 independent tertiary proteins that have all come together to do group work, right? To do a bigger job. Okay, and so as you can see, this is the structure of a heme unit. Okay, aka it's a blood cell. Okay, so your blood cells create what's a basket, and this even looks like a basket here, right? And it carries a cell of iron in the center, and that iron binds to oxygen and carbon dioxide. It's pretty lit, okay? That's a big job, okay? And it's so big that one individual tertiary protein cell can't do it on its own, or molecule can't do it on its own. So they all have to get together, okay, commute as a group to do the job. Okay. So the way these guys are linked, right, so these guys have to be bonded together. These guys have to be bonded together, right? So we have bonds between each of our links. Okay. These bonds have to be super strong. Okay. If I'm going to create a basket that's going to hold iron, and that's got to be strong enough to be able to carry around the oxygenation that's going to keep my organism or cell alive, that is not a loosey-goosey bond, right? So I have to pick one of the 2 strongest bonds in chemistry. Okay, and there is a little bit of variety here, so it's either going to be a hydrogen bond. So remember, those are the O. Come on, man. That's one. O to H bonds. Okay, or an ionic bond. And that's the positive to negative bond. Okay, so those bonds are very, very strong. And so that'll ensure that our structure here is held together. Okay, so in this case, you've made the horrific mistake of sticking 2 sets of earbuds in your pocket, and they've come out horrifically clumped and horrifically intertwined. And there's certainly no bond stronger than cords that have gotten intertangled. My handwriting is atrocious. All right, any questions on this? All right, and then same deal, right? If we break this apart, we can go back down to the tertiary level, right, and so on and so forth. Again, we're deconstructing our Lego tower. So in this case, we've put 2 towers together, right? Linked them by a catwalk or something. I don't know. It's a fancy Hogwarts castle or some business like that. This feel okay? Okay, so remember, the key here is all along, structure determines function. So the shape that we're creating is determining what these proteins are doing. Okay, and this is so important, and why this has taken so much to create our functional proteins is because proteins do so much. They're our favorite biomolecule. Okay, and we can alter these structures by breaking these bonds back down, right? We can just take our Lego towers back apart. And you break a chemical bond, or a bond by chemicals, you can alter the pH, for example, or you cook it. Okay, which for a cell is a very small temperature change. But also, for the record, that's why fevers are so problematic. Not super great for your cells in your body, but also kill bacteria and viruses, which is why your body has a fever. It breaks bonds. It's your body murdering the bad cells in your body. Okay, any questions before we do our summary? Feel okay? Okay, let's do our study guide for this then. Okay, so bring out your piece of paper that you've been working on, or of course bring up your file. Okay, so we're going to add, I'm drawing here. We're going to add proteins, right, our third, that's an E, level to our participation activity. And as usual, we're going to have 2 bullets, but this was big, okay? So our bullets are going to be fuller than usual. So our first bullet, you're going to give me 2 things that proteins are used for. We've got a pretty big list. Okay, so you just need to give me general things to use proteins for, but your list has to have 2 of them. Okay. Your second bullet point, okay, I need you to give me 2 things that would allow you to identify a protein or an amino acid. Okay. Remember, do your best to try to fill out your study guide without looking first. Okay. It's a really good practice to study tip. Okay. So try to recopy your notes. Try to fill out your cheat sheets and your study guides without looking. And then when you get stuck or after you've done it, then go back and check yourself.
So really quick, there's a question in the chat.
Sure.
Is the primary level the only level that uses dehydration synthesis?
Absolutely correct and great question. The primary level is the only level that uses dehydration synthesis to create peptide bonds. So that's the only level that's going to feel similar to our carbohydrates and our lipids before. Great question. The rest of you can go.
What was the question?
So it's just the in-class.
Oh.
The in-class. Yes, ma'am. Great job today, Miss Lafferty.
Thank you.
What I would do without you, it would be so hard to run both of these things.